class. Welcome to today's lecture. My name is Bera Robinson. For those who don't know me, I'm from the Department of Electrical. Maybe you've not met in your previous classes, but we are going to meet in this class of microprocessor systems. So feel free to join. This is what is called blended learning, whereby we are going to have some class online and others are going to be physical. So the physical class is going to follow up what we are doing online. So make sure you always follow what we are doing online. Be active in your WhatsApp group. Be attentive. I will be sending some links. These links can be of notes. These links can be of podcast, or they can be of the recorded video. So most of the video we are going to do is going to be recorded, but towards the middle or towards the end of the term, maybe we'll be doing also some live sessions online apart from the physical classes which we'll be having. So today we are going to do introduction to microprocessor system. I'm going to take you through the course outline so that we understand what we are going to be expected to learn or to know at the end of the unit. Please welcome and enjoy. Now, you maybe you've asked yourself this question: what is a microprocessor? So microprocessor, it's an IC. It's an IC which contains a CPU and other functional blocks. Things like arithmetic unit, things like registers, things like memory, buses. All these components are packaged inside an IC. We are going to see that IC soon. Now, what is the difference between this IC, that is microprocessor, and any other IC? Remember, IC is short name for integrated circuit. So it means that we are putting a circuit inside an IC. Now, the difference between microprocessor and any other IC is that the IC which is microprocessor, you can program it to do any function. But the normal IC, which we normally refer it as hardwired IC, you cannot program a hardwired IC. For example, 555 timer, it's an hardwired IC, so you cannot program it. But Intel 885 is a programmable IC, so it means that you can change its functionality by writing a program. Most of the time, these programs are written in C language or machine language or mnemonics. We are going to see what are they as we continue towards down the lesson. So the Intel 885 is an 8-bit microprocessor which was designed and manufactured by Intel, and it was released to the market by March 1976. That's a long time ago, isn't it? Yes. Yeah, it's a long time ago. But now it influenced, actually, even now how microprocessors are being designed. They are designed based on this architecture. So not much has changed. We've only added some functionality to the microprocessor and also the speed and the capabilities. But the infrastructure almost maintains the same since 1976. What we say it's an 8-bit microprocessor. It's an 8-bit microprocessor because it's going to process 8 bits of data every time it does execution of that data. So whether we are moving data from the memory to the arithmetic unit, or we are moving it from the arithmetic unit to registers, we are going to move this data in 8-bit. So, of course, this was not the first microprocessor which was designed by Intel those days. We had a previous version which was actually more popular, but it was a less powerful compared to 8085, and this was Intel 8080. And that's why you said it was an enhanced and more integrated version of the earlier 8080 processor, requiring less support hardware and only a single 5-volt power supply. And that's true. This microprocessor, Intel 8085, uses only a single power supply, which is 5 volts. This simplifies the design of this Intel 8085 when you want to come up with microcomputing environment. So all these technologies, we can say they are obsolete, but we still find them in things like a bread toaster. You can still find them in old calculators. Yeah, Intel 8085. But we don't have much use for it in the modern world. Of course, we have more powerful microprocessor which came to replace Intel 8085, and they are even cheaper nowadays. Now, the picture which I'm showing you, this is the picture of the IC, how it appears physically. So figure 1, this one, shows how the IC appear in physical world. So this black body you are seeing, this is a die. It's a die. So it's a die from a silicon wafer, which this chip was fabricated on. What you are seeing here, these are the pins. These pins, they connect inside the IC. So it means that inside the IC we have small wires. Those wires, we normally call them buses, and they are connected to these pins so that you can access them in the outside world. The picture on the right side of this of your screen is a pinout diagram. This figure, which is figure 2, shows the pin count of Intel 8085. We have a total of 40 pins. You've seen, we count them clockwise, anti-clockwise. So this being the first pin, you go downward to the 20th pin, then from 21st to the 40th pin here. And all those pins have their functions. Their functions are actually indicated using the names. For example, we have pin 1 and pin 2. These are X1, X2. We are going to see what are their function. And then we have pin, for example, pin 12 to pin 19. It has been written AD0 to AD7. Those are data bit. Those are data pins. We use these pins 12 to pin 19 to transfer data. Pin 20 and pin 40, this is for connecting the power, 20 being the ground, 40 being the positive supply, which goes up to the 5 volts. For example, we have another pin from pin 21 to pin 28. These are A8 to A15. These we call them address pins. Address pins. The work of these pins is to carry the address. So if I want to carry an 8-bit address, I use A8 to A15. If I want to carry a 16-bit address, I have to combine the address pins, which are 8, plus the data pin, which are 8. They form this makes a total of 16 pins. We are going to see the work of other pins. We normally say these are control pins, RD, WR, LE. Those are control bus. We have status pins. These are pins which indicate status of what the microprocessor is doing. These are something like S1, S0. We have interrupt pins, which we can use to interrupt the microprocessor, or the microprocessor can interrupt other components in the microcomputing environment. And these are pins like sorry. These are pin like RST 7.5, RST 6.5, intra, trap. All those are interrupt pins. So this actually the pins of the microprocessor, and we are going to learn how to use them. The next diagram, which is figure 3, this one shows the block diagram of what is happening inside that IC. So you've seen we have the IC, the physical IC here, the pins and their representation. Now inside this IC, this die, we have these functional block diagrams. So we have what is called interrupt control, we have serial input output control, we have instruction registers, we have general purpose registers, we have special registers like stack pointer, program counter, we have accumulator, which is another type of register, we have arithmetic logic unit here, we have timing and control block here, address buffer, data stroke address buffer. These are the functional blocks which you can find inside any microprocessor. It doesn't mean that this is only for Intel 885. No. For any microprocessor, they have at least to have this basic. But of course, based on the microprocessor, if they are advanced, you will find that these components are either more powerful. If they are registers, there are more registers. And maybe we've added some special functioning blocks to modern microprocessor, like processor for doing calculation of maths. We have processor for AI. We have processor for processing digital signals. We normally call them DSP processors. All those are processors which they are special processors containing these basic functional blocks, but actually we've added some other special blocks. So most of the time in this unit of microprocessor, we are going to spend our time inside this block diagram. So you'll be confused sometimes. You might think that we are studying something which is outside the IC, but I'm telling you, don't be confused. All these are inside what? That IC. That's why we say it is an integrated circuit. Now, I'm going to show you a picture which doesn't make sense as of now. This is picture. Yes, this is figure 4. It's a CPU die. So inside that physical appearance of the microprocessor, inside that black thing which I told you is a die, we find this masterpiece. This is a very dense world. All these things you are seeing are very, very small. We need a microscope to zoom them. Our registers are here. We need microscope to zoom them. Yes. The buses, what you are seeing are like small lines. Those are buses. These are buses. We have the registers in here. We have the arithmetic logic in here. Actually, it was made using 75,000 transistors. Yeah, it's a lot, but it's very small compared to the current numbers. Currently, we are making CPU using billions of transistors. Yes. So you can imagine the difference in technology from 1976 to current. So 1976, this is a total of 75,000 transistors. But now we make CPUs using billions of transistors, even 50 billion transistors. That's a lot of components. And they all fit inside this die. So what you are seeing, these are the pins which you are seeing them from the outside. So inside, these pins have been terminated in the die, but outside you see them being aligned sideways. But when you see here, they are all over the die. Yes. So this is how we connect the pins to the die. There's not much you can see because it's not a high resolution photo. You can always go to the internet, check for high resolution photos. Go to the YouTube, you will find videos explaining these CPU die. Don't worry, things are going to make sense as we continue with our lesson. Now, before we start this course officially, it's good for us to know what we are expected to cover, and I'm going to take you through the course outline. I'll share this presentation with you so that you write down these topics. So I've broken this course outline into two things: the learning outcomes and the activity you are supposed to perform or to carry out at the end of the topic. For example, the first topic, which is Unit 1, is microprocessor architecture. So we'll be learning about it. We'll be going through explanation of different operations of microprocessor, including what is timing. We'll describe what is a machine cycle or instruction cycle. We'll identify addressing modes and instruction types, and then we are going to distinguish between machine and assembly languages. So the activities you will perform at the end of this unit include: you are supposed to draw what is called timing diagrams for machine cycles, simulate instruction execution using basic opcodes. You have to compare addressing modes with examples, and then write simple assembler programs using directives. So that is the architecture of the microprocessor. And then topic number 2, which is Unit 2, we are going to dive deep into programming, and this is going to be introduction to assembly language. Assembly language is a very big topic, as we are just going to do some introduction to it. Doesn't mean that you will not learn anything. You'll be able to come up with programs, simple instructions, which you can actually develop. Under that, we are supposed to understand the structure and the syntax of assembly language. We are going to see that we have what is called an operand and the opcode. So opcode being the instruction which is going to perform the work itself, and then the operand is the data which we are working on it with that instruction. And then you will apply data transfer and control instructions. We are going to see how to transfer data between memory to registers, between registers to memory, between registers to registers, between registers and input-output devices, or input-output devices and the memory. Then we are going to use assembler directives in program development activities. You are supposed to do code basic input-output routines and note assembler programs for clarity. Practice programming cycles using emulators or kits. Unit 3 is going to be about input-output methods. You see, microprocessor, sometimes we need to connect it to the outside world, and those outside world, we call them input or output devices. So these devices are the one which are going to provide data either to the microprocessor or take data out of microprocessor. So we have different methods of actually interfacing the CPU, that is microprocessor, to the input-output devices. So we are going to see those different methods. So we are going to differentiate between a programmed and mapped input-output, explain handshake control input-output mechanism, and we have actually other, which is POL input-output. The activities: you are supposed to design input-output flowcharts for different methods, simulate handshake protocols using LEDs and switches, compare mapped versus programmed input-output in a tabular form. And then Unit 4, of course, is going to be about interrupts. Microprocessors, sometimes you need to interrupt them to do other things apart from the main program, and thus we are going to discuss them under Unit 4. So we'll describe between polled versus interrupt-driven input-output, and then we are going to identify types of interrupt and their operation, including the priority of those interrupt. Those are the activities you are supposed to do under this unit are demonstrate interrupt handling using microcontroller kits, create flowcharts for interrupt service routines, analyze timing difference between polling and interrupts. So Unit 5 will be about direct memory access. Sometimes we need to access memory of the microcomputing environment without actually disturbing the microprocessor. And that mechanism is called direct memory access. Why do we have to do that? Because it improves speed. You can actually transfer data between the input-output devices and the memory at higher speed. And then we are going to look at the activities, which are diagram for DMA architecture. We are going to simulate DMA transfer using virtual tools. And then we are going to compare CPU versus DMA data handling. How do we handle data when we are using the CPU? Like the CPU is going to be like the controller here. And how do we handle data when we are accessing the memory directly using what is called DMA controller, the one which we've seen here. And this has made it possible for us actually to transfer huge amount of data. For example, if you have a flash disk or an external hard disk and you want to transfer huge amount of data between between your computer and that flash disk, the CPU will not handle that data transfer. We normally leave that one to a special controller called direct memory access controller. And then the next topic, which is 6, we are going to discuss about interfacing devices. This is how we are going to interface the external devices to the microprocessor. So we are going to identify internal and external device interfaces. We are going to explore tools for assembly language programming. And then activities we are going to do is interface sensors or display to microprocessor kits, document interfacing procedure, evaluate tool chains for assembling development. Unit 7, this is about microprocessor software. We are going to discuss about software development tools. We are going to understand features and application of microprocessor softwares. And then we are going to do some activities there. We are going to review what is integrated development environment, IDEs. So I'm going to teach you what is an IDEs, and then what is a simulator. And of course, we are going to use this environment to develop our program. And then we are going to compare software tools in terms of usability and features, and then document a sample development workflow. We are going to look at tools in assembly language programming, use of parallel ports and programming tools, apply documentation procedures in assembly development, and then the activities which are going to follow up are this. Unit 9 is going to be about control structure architecture, and those are the learning outcomes: understanding programming control structures, analyze microprocessor control levels and programs. The activities you are going to perform here are design control flow diagrams, implement control logic in assembly, and then compare control levels across microprocessor families. Unit 10 is going to be about microcomputer development. Now, Unit 10 is actually what most of us will be seeing in Unit 1. When we are discussing microprocessor architecture, people will be seeing what we are supposed to discuss in Unit 10. Unit 10 is when we are taking that microprocessor and we want to build a computer. But of course, we cannot build a whole computer because that requires a lot of many years of study. So we are just going to build a small computer, not even a small, a microcomputer. So in this microcomputer, we need at least to have a microprocessor, which is going to be our CPU, memories, and then RAMs, input output devices, which are going to be to provide ports, and then we are going to connect input output devices to those ports. Yeah, so that's a microcomputer environment, a small computer which can perform basic things like a calculator which can add two numbers. That's what we are going to look at unit 10. So we are going to identify development aid and kits, apply development tools in educational settings. We have actually training kits which are built using microprocessor 885. I'm going to show you when we meet for physical class. Activities which you are supposed to perform is to explore microcomputer kits and their application, document use cases for development aids, then simulate educational scenarios using kits. The final topic, which is unit 11, is going to be about application of microprocessor. So we are going to see microprocessor in how does it perform in real world when it's handling task, and we are in that space. We are going to be able to see some diagnosis. How do we do diagnosis of microprocessor systems? How do we apply fault finding methods effectively, among other procedures which we are going to see. So the activities here, you are supposed to perform fault simulation and diagnosis, create fault trees and troubleshooting guides, conduct lab-based fault analysis exercises. So that marks the end of the first lesson, whereby I've taken you through the introduction to microprocessor for you to understand what is this microprocessor system. I've also taken you through the course outline, what we are expected to learn during this course. In case of any question, in case of inquiry, you will always reach me through your class rep. This video, I'm going to share the link with your class rep so that he is going to share to the rest of the class. Make sure you watch this video. We are going to have a follow-up activity. Make sure you work on those activities. We will be meeting for physical class on Friday. I think we have a physical class Friday, but Mondays, most of them will be an online class, either a live online class or a recorded video. Thank you for having patience up to the end of the lecture. These lectures are going to be probably 1 hour at most. For example, now we are going to go up to maybe around 30 minutes. Most of them, they are going to be around 1 hour long. I think other communication will be communicated to you when we meet for a physical class. Otherwise, enjoy your day, and microprocessor is not that difficult, so don't fear. Thank you so much.